Record. Okay, so you had a question related to this problem. Oh, dynamic programming, depth first search. So the idea is that if I want to compute, say, the longest path, I define longest of v to be the maximum length of path from v to whatever my target node is. And this is going to be either 0 if v equals t, infinity if v is not t and v is a sinc, and otherwise it's going to be the max over all edges from v to w of the length of the edge from v to w plus the longest path from w to t. So yeah, that's it. You basically, one way to think about it is if you run through the entire algorithm, you're going to examine every single edge in the graph once and spend constant time on it. So the running time of this algorithm is going to be proportional to the number of edges plus the number of vertices, because you spend constant time doing work on the vertices. Yes, longest path in general is NP-hard, but in DAGs it's not. So special cases of NP-hard problems can be easy. We're working in a DAG. I mean, every edge points from an earlier time to a later time, so there can't be any cycles. Yeah.
That's a good point from the lecture on approximation methods.
Okay, so are there any more questions about taking the bus, general graph modeling things? So we have a call to do approximation algorithms. You want to do NP hardness? Let's vote. What do you want to do? What do you? Sorry? Okay, we got what have we not done? We've done some graphs. We've done some dynamic programming. We've done some stuff. We've done some randomization. So we haven't done flows. We haven't done linear programming. We haven't done any NP hardness. And we haven't done any approximation algorithms. Are we missing anything else? Okay. So, you wanted to, let's just start with approximation, since I think that was the first one that was called out. So do you have a specific approximation problem in mind? Yeah. Okay. So I have a network which is composed of a cycle of n nodes connected. Well, it's a cycle, so it's connected in a cycle. And I have a bunch of calls where each call I have a source node and a destination node. Okay, so I have a call. Say I want to, I want to send some information from 3 to 7. I want to send some information from 6 to 45. I want to send some information from 5 to 17, and so forth.
So for each call, there are two possibilities for how I could route the call. If I want to go, say, from 1 to 5, I could go in clockwise order or increasing order around the cycle, or I could go in counterclockwise order around the cycle. Okay. And my goal is to route these given calls to minimize congestion.
I'm sorry, I need to look at the precise objective value again. The overall load on the network. Okay, so
The congestion I'm going to define as the sum over all edges in the network of the number of calls that go through that edge. This is my, my objective value. Oh, sorry. That's exactly why I wanted to look. I want to minimize the maximum over all edges, the number of calls through the edge.
if I want to minimize the sum, then I just, for each call, I just say which way is shorter. Because the sum over all edges of the number of paths that go through the edge is the same as the sum over all paths of the number of edges the path goes through, which is the length of the path.
But here I want to minimize the max. Okay. And so the problem asks find a two approximation algorithm for this problem.
Okay. So, as usual, when we're trying to find a two approximation algorithm,
So remember, the goal is eventually to be able to say something like this, where
I need to find some function of the input that I can squeeze in between these two as both an upper bound on the cost, the objective value that's the solution is generated by my algorithm, and at the same time serves as a lower bound for the optimal objective value here. Okay?
So let's try first to figure out, is there a way that we can find something that we can use as a
lower bound. Opt is at least something.
So any ideas, what we could write here?
Not necessarily. So maybe my calls are 1 calls 2, and then 3 calls 4, and then 5 calls 6, and then 7 calls 8, in which case my maximum congestion is 1. Remember, I'm not summing up over all the edges. I'm saying for each edge, I want to put a cap on the number of calls that go through that edge. Yeah?
Where's this problem?
The lecture notes on approximation algorithms. I think it's number 7. Yeah.
How about the value if you just went clockwise for all of them? The max value?
Well, if I go clockwise for all of them, that's going to give me upper bound on opt, because that's actually a way I could route the calls. That might be A of X. I mean, one thing I know, because I'm trying to do a minimization problem, is we know that A of X is bigger than
OptiveX. So OptiveX is the best possible call routing we can have. But I'm willing to bet that this problem is NP-hard because every interesting problem is NP-hard. But we want to lower bound. Yeah.
You can add all of the shortest path for all of the calls, then divide by n.
Oh, okay. So this is the at least the average. So why are you dividing? So I'm a little confused here. Can you say this again?
So you get the shortest path for each call, then you add them all, add everything and divide by n, because that's basically like the number of times we go around the whole cycle.
Right. So okay. So let's imagine. Right. So this is the shortest path length for my. So suppose I just imagine that congestion is a fungible. It's a continuous resource that I can distribute across all of my edges. Essentially, what I want to do is replace this max with an average. Right? And if I want, an average is 1 over n times the sum, and I already sort of argued that if I want to minimize the sum, I should send every call along the shortest path, whichever, clockwise or counterclockwise, whichever goes to the fewer edges. So I'm going to take this distance, summed up over all calls, and then divide by n. Okay, so this is a reasonable lower bound, where n here is the number of nodes, not the number of calls. I'm averaging over edges, not averaging over calls. So I'm in my head, I'm trying to make this up as I go, in my head trying to get the analysis to converge with what I think the algorithm is. So maybe I should try just going at this from the other direction. I'm going to guess the algorithm. So the algorithm is always route clockwise. Every call goes the same direction around. Now, why should that give me something good? I hope at this point it is obvious that this question is not on the exam. Possibly.
Because at least some number of the paths will be less than n over 2, which is shorter than
Yeah, maybe this is what you want to do, is to actually, I'm going to guess the algorithm, which is route all the calls one way, route all the calls the other way, take whichever one is better. And then argue that the sum of these two, yes. There we go, here we go. All right, so for each call I can route it one way or I can route it the other way. Okay, and the sum of those two, I know what the cost is, right? The sum of those two, the cost is going to be n. Right, so for any pad, the two paths together have length n, So if I imagine just being sort of crude about this, I try routing everything clockwise, try routing everything counterclockwise, take one or the other. What congestion am I going to get? Yeah. Sorry?
So say you have, so you're doing one of these approximation problems, right? You
Yep.
have an idea for an algorithm that you think might be the answer, but then you find an example where if you did it your, like the worst case, you could be like way above optimal. Would that just prove that your guess is wrong?
Yes.
Okay, so in this case, if all of the paths were supposed to be one step counterclockwise, and we flipped it the other way,
Uh-huh.
and make the max much larger, so this would not be the question.
Right. That's exactly right. So if in fact the optimal solution is this, like every call just happens to be to one step counterclockwise, then here the optimal bandwidth is 1, but this approximation algorithm would give you a bandwidth of, or a congestion or whatever it is of n minus 1, or n minus 1. So this is not the right answer. But if I say either clockwise or counterclockwise, whichever is better, that might work. Another possibility for a reasonable approximation algorithm is, let's try routing each call along its shortest path no matter what. Another one is for each call, route to increase congestion as little as possible. So if by routing clockwise, you increase the congestion on the worst edge, but by routing counterclockwise you don't, then you should route counterclockwise. So you're trying to keep everything balanced. I think actually the last one is probably the algorithm that we're really looking for here. Yeah.
Two things. One, could you go for like approximation algorithm that had like possibilities, but also like, could you just have a set of n calls all between two nodes where like there's node and then a node in between and then the final node, and the shortest path would just put all of the load on that one then, as opposed to dividing like half the calls routed this way and half the other.
Well, see, that's actually good, because you just described a case where the greedy algorithm is only twice as bad as the optimal algorithm.
Oh, right, yeah.
Right? So there's there is some possibility that shortest really is the right answer.
Yeah.
Because, as you said, if you try to imagine some cases where instead of writing all m calls along the same edges, you put m over 2 this way, m over 2 the other.
Yeah,
Right.
so more than 2 times exactly.
Yeah, exactly twice as bad as the other. So, punt. This is not going to be on the exam. Let me describe another approximation algorithm. This is also not going to be on the exam, but which was almost on the exam. Let's suppose that I have a bunch of boxes that I want to load into bins. These boxes have various weights, and I'm allowed to put a certain maximum weight inside each bin. Okay? And I want to minimize the number of bins. So I want to pack these boxes into bins such that the number of bins is minimized. This is sometimes called the knapsack problem, or this is a special case of what's sometimes called the knapsack problem. Okay. So, I want, in fact, now I want to find a two approximation algorithm. So again, I have the packing computed by my algorithm, and I want it to be twice the optimum packing, and I need to find some function of the input size, some function of the input that I can squeeze in between. So are there any things that I could say opt is bigger than? Right, so I know that opt is going to be bigger than the sum over all items of the weight of that over the capacity of the, the capacity of the bins. Right, this is just, the objects are not actually boxes, they're amounts of water, and I pour them into the bins and possibly splitting them across multiple bins. Okay? All right, this is in fact what I need. So, what would you do if you had to solve this problem? Okay, sure. Why not? Let's sort up or down. You know, decreasing weight. Okay. Great. So let's imagine that they're sorted, and now what do you do? What does that mean?
Choose the largest one that you can put in there and then the next largest one.
Okay, so there are a couple of possibilities. Best fit. All right, so this means for I goes from 1 to n, put item I into the emptiest non-empty bin, or add a new bin if item I doesn't fit. Into any existing bin. There's another possibility. I'm going to set j to be equal to 1, and now for I goes from 1 to n, if item I fits, put it in j, else j gets to j plus 1, and then put item I into bin j. So fill up the bin as much as I can, and when I can't put anything in, send it off to UPS and then start filling the next bin. Yeah.
Why would that fit put the biggest item in the first bin and then put the item that's closest to the bin's remaining capacity?
That's just what that algorithm is called.
Okay.
That this traditional name. What you're describing is a different approximation algorithm, which is try to fill bin 1 as best possible, then try to fill bin 2 as best possible. It's probably also called best fit by a disjoint set of people.
Okay.
It turns out both of these are two approximation algorithms. But this one is a little bit easier to analyze. Because, in fact, it has a one-line analysis. So the claim here is, at the end of the algorithm, at most, one bin is less than half full. Okay.
So suppose there are 2 bins that are less than half full. Why did you put anything in the second bin? QED. In fact, that also works for best fit. Right? All of the items that you put into the later bin that's less than half full, you could have put into the earlier bin that was less than half full. Yeah.
I'm sorry, what's the difference between A of X and F of X? It's like,
A of X is the solution that your algorithm computes. F of X is some function that you're using for analysis as an intermediary between your solution and the optimal solution. In this particular case, F of X is what you would get if you could subdivide the boxes into tiny little pieces. And opt is the best, F of X is the best fractional solution if you want to think of this in your programming terms. And opt of X is the actual optimal discrete solution. Right. So this lower bound is what you would get if every bin except the last one were completely full. Right. In fact, I can do this. Right. So this is the solution you would get if you could fill every bin to the top except possibly for some leftover waste at the end of the one last bin. Right. So on the other hand, both best fit and first fit, you can guarantee that every bin is at least half full, except possibly the last bin. So if the optimum uses k plus 1 bins, where the plus 1 is the extra thing that's left over, then this algorithm uses at most 2k plus 1 bins. 2k plus 1 is less than twice k plus 1. Right? So here I'm saying that if I sum this up, A of X is at least, half. Actually, the right way to say this is A of X is at least 1 plus half of this sum. Sorry, that should be less than or equal to. Okay, so this is what you would get if you filled each bucket exactly halfway, and then I have one left over. But I'm filling each bucket at least halfway, except possibly the one left over. So I'm using fewer bins than what I would get by cutting everything in half. But now I know that sorry, I shouldn't say half here. I should say 2. This is at most 1 plus 2 opt. And yeah, for that, I don't really care that there's a plus 1 there when I'm doing the analysis. The ratio is as close to 2 as you want.
so the reason it's 1/2 is because we fill it until it's not possible to fill anymore.
Right, I fill it until it's not possible to fill anymore. If at this point it's less than half full, then whatever the last object I put in had weight less than half of the capacity of the bin, which means the next object I would put in also has capacity less than half of the bin, which means I should put it here, unless I'm done.
So we didn't even need to sort it. Right?
That's correct. We didn't even need to sort it. I mean, this argument actually works even without the sorting.
So would there be a tighter bound sorting?
I think actually decreasing first fit or decreasing best fit with a little bit more care, I think you can get it down to 3 halves, but I'm not 100% sure about that.
That's 3 halves.
Yeah.
And there's a strictly way to get it down to like even better.
Yeah.
Well, no, it's less than 3 halves plus an additive constant.
Yeah, this is really 2 plus an additive constant, but whatever. We're not going to worry about the additive constants. Yeah. Okay, so let's call this sum K. Right. K is the number of bins that I can fill up completely to the brim if I chop all my boxes into dust. Okay? 2K is the number of boxes I can fill
halfway
Oh,
if I fill everything in dust. So if I fill everything exactly halfway, and then I have a little bit left over, I'll use this many bins. But in fact, my solution fills every bin more than halfway, and so I must be using fewer bins. Well, because there's this argument about the last bin. I'm being conservative here. All of the bins except the last one are half full. And the number of bins except the last one is at most twice up. Yeah.
Could you explain how this works unsorted?
I think maybe for unsorted, I think unsorted this works for best fit.
Yeah, would you have to check the previous boxes to see if
For
it's there?
first fit, if it's unsorted, then no, this argument doesn't work.
Yeah. Okay.
But there's a separate argument that says any two consecutive bins together carry the amount of weight of a single bin. So you still get a 2 approximation.
Okay.
Okay. Let's move on. Yeah. Okay. So this is one of these magic self-reduction problems. I have a box where I can feed in a graph, and it will give me the length of the shortest traveling salesman problem. The shortest traveling salesman tour. I want to use this as a subroutine to build actually construct the tour. Okay, and I should be careful here. I'm going to call this with a different graph than the one I'm given as input. So this is like the 3-color problem that we did in the homework, where I'm going to modify the graph, call the oracle that gives me the TSP length, which is one of these random magic things. I don't know how they work. But I want to eventually get there's a rainbow, so it must be magic. Okay. I know that has got to be the world's crappiest rainbow, but whatever. So what we need to do is somehow modify the graph so that the call to the TSP length oracle tells us something. What we're eventually trying to focus down on is a set of edges that are in the tour. So I can imagine a question that I could ask is, does the shortest traveling salesman tour go through this edge or not? There might be multiple traveling salesman tours, in which case I might be asking, does every shortest traveling salesman tour go through this edge? Or does at least one shortest traveling salesman tour go through this edge, or not? So how would I figure this out?
Could you modify the edge weight by some small amount, smaller than the difference between it, and see if the weight you get back goes down by that same amount?
How much?
Well,
Okay, so somebody else has another idea, which I actually think is going to be a little bit simpler. Okay, so suppose that the TSP length of G is equal to the TSP length of G minus some edge E. So I just delete the edge. And it tells me, well, same length. What do I learn from this? that I don't need that edge to have the same traveling salesman tour length. So then just discard that edge and recurse. Okay. Otherwise, well, suppose the TSP length for G is smaller than the TSP length for G minus E. Now what do I do? Right, I somehow need to keep this edge. Yeah. Well, okay, so one possibility is, okay, whatever.
Yeah.
Right? And in the end, what this means is that if I'm in this case, then every shortest Hamiltonian cycle goes through E. And in the first case, it is not true that every shortest TSP path goes through E. So I throw E away. So after I do this for all edges, what edges am I going to be left with? Right, every edge that I keep belongs to every TSP cycle in the graph I have left.
No. If just like if you only have one edge left, one cycle left, you will have such things, right?
Right.
If you have two, you can still delete one.
No, I'm going to call this for every edge.
Okay.
Right? For all edges E. Right? So in this case, I'm going to say G gets G minus E. Now my algorithm is if. Okay. So how can I? What am I going to be left with at the end? The only edges that can survive to the end are edges that belong to every traveling salesman tour in the graph at the end. In other words, I'm going to be left with a cycle of minimum length. It's a Hamiltonian cycle in the original graph. At this point, I'm done. Yeah.
So, because the edges that we're describing here are edges that are not necessary for every single traveling tour. What if there, I guess like,
Okay, so suppose there are multiple traveling salesman tours. Some of them go through these edges, some of them go through those edges. When I look at an edge over here, if I can throw this away, well, there's still a shortest traveling salesman tour that goes through these edges, so fine, I can throw these away. So if there are multiple shortest tours, I will throw away an edge from one of them, and I'll leave a smaller number of them behind.
also converge on the one.
So over time, you'll converge down to a single TSP tour.
This would be like the same algorithm.
Yeah, so if you were given a black box that just says, is there a Hamiltonian cycle? And then you want to construct a Hamiltonian cycle, you would do exactly the same thing. If throwing away the edge doesn't destroy the Hamiltonian cycle, fine, throw it away.
Can you do an edge contraction and then recurse out?
Yes, you could also do this. You could say, once I know that the edge belongs to the TSP tour, contract the edge down to a single vertex, throw away any loops because they don't matter, and now recurse on this smaller thing, and just remember which edges you contracted. Or you could take an edge that you know belongs to the TSP tour, set its weight to something really small to guarantee that every TSP tour continues to go through it no matter what else you do. Or instead of deleting, you could set the weight to be really big. right? So this is a little bit easier to think about than the suggestion you had, which was take the weight and just tweak it a little bit. Just no, take the weight and send it up to infinity. But what you said would also work. It's just that you need a different way of locking the edge down.
Okay, so I understand this is using algorithms that compute something that we have.
Yeah.
But what if we only have a one-time information of how long it is, and then from that we have is there a fast way to do that?
There is in principle, but it requires a bit more setup. In particular, you're not actually going to be calling. I mean, so at one level, yes, because these problems are all NP hard, and this is an NP optimization problem versus an NP construction problem, and there are reductions between any pair of these, right? I think it's a little bit easier maybe to think about what happens with the coloring thing. Basically, you set up in advance a bunch of graphs that sort of like, okay, I've got this big for loop, so I'm going to make many, many copies of the graph, simultaneously query all of those copies by making one call to the oracle. And then you carefully reassemble the answers. Off the top of my head, I'm not exactly sure how you would do this for TSP. Because one call would, assuming you could glue the graphs together so the TSP tour goes through all of them, you would still only find all the edges that belong to every traveling salesman tour, not edges that might belong to some but not others. So I'm not entirely sure how you would do it in this case, but there are sort of general purpose results that imply that you can.
I think okay, so that's like using only one call, but what if we just found this number on the hard disk, like the 593, and then from there.
Oh, no. So that problem is actually still NP hard. So if I tell you, here is a graph, here is the length of its traveling salesman tour, find its traveling salesman tour. That problem is still NP hard because if you had an algorithm to solve that problem, then you could compute the actual traveling salesman tour for a graph where you don't know the length, essentially by doing a binary search over all possible lengths. Right.
Show us a full credit answer for this question.
I'm sorry?
Could you show us a full credit answer for this question? Like this 4 line is it worse for 2 point? Or you can add something else?
Unless it asks for a proof, then yeah, that's an algorithm. If it says describe an algorithm to do this in polynomial time, that's an algorithm. It's pretty clearly polynomial time. Yeah.
And that was
Yeah. Yeah. Yes.
Could you prove how three-way partition is NP hard?
Which one? Sorry?
Three-way partition.
Okay. So I assume this is, you're given a set X and you want to split it into 3 disjoint subsets A, B, and C such that sum of A equals sum of B equals sum of C. Right? Good. So what am I going to reduce from? Well, okay, yeah, I could reduce from 3 sat because there's a 3 in there, but that's sort of a fallback answer. Is there any other problem that has a smaller edit distance to 3-way partition? Two-way partition, otherwise known as partition, right? So remember the partition problem is I'm given a set X and I want to know whether X can be split into 2 sets with equal sum. So somehow I want to modify X into a set Y such that y can be split into 3 sets with equal sums if and only if x can be split into 2 sets with equal sums. Okay, so y equals x union what? Yep.
You just introduce another element that's like the sum of half of the sum of all values.
Yes. What if the sum of all the values is odd? Okay, fine. So I double every element of x. That doesn't change the answer to the partition problem. Then I take a new element whose value is the sum of all the elements in the original set x. And I add that one element, and now I have a set y. And now, if I split this into 3 parts, each of those parts, the sum of the elements must be equal to the sum of the original elements in x. And so one of those parts must be this singleton, and the other 2 parts must be a partition of x. Yes? Well, formally the problem says I'm given a set of integers. What? Oh, good point. If the sum of the values in x is odd, what do?
False.
You say no. Okay. So in this case, the reduction actually has a branch where we go odd, and then we just bypass the subroutine entirely. That's perfectly reasonable as well. Yeah. No, 2x means double every element of x. Multiply every element of x by 2, not duplicate every element of x. Yeah. Yeah. I'm happy to go until 3:30 unless someone kicks us out. Okay. But then at 3:30 I do have another part of my job to do. Yeah. It's posted. Sorry. Look for the file that talks about rubrics. It's whatever URL/exam/rubrics.pdf. So generally the rubric is going to be 4 points for the actual reduction and 6 points for the proof. Which, of course, 6 is equal to, 3 plus 3. 3 points for the if part, 3 points for the only if. Yeah. So the graph like this tells me the overall structure, but you need to tell me what happens in this box. And the easiest way to tell me what happens in this box is to say, this is an algorithm that takes in a set x and produces as input and produces a set y as output. So describe that algorithm. You can describe it in words, you can describe it in pseudocode. I don't care as long as it's clear and unambiguous. Yeah. Sure. So let's walk through the if and only if for this particular one, since just to see what the structure is. So proof. So there are 2 parts. Suppose x can be partitioned. Okay, so x equals A union B, where sum of A equals sum of B. Then sum of A equals sum of B equals the sum of all values in x divided by 2. So y can be 3 partitioned. other direction. Suppose y can be 3 partitioned. So I'm going to write y equal to A union B union C, where sum of A equals sum of B equals sum of C. This is going to be, of course, equal to the sum of y, all values in y divided by 3. But by construction, this is equal to the sum of all values in x divided by 2. So without loss of generality, C is equal to this singleton set containing this element that I've added, sum of x over 2. And therefore, A union B equals x, so x can be partitioned.
So this is a proof that x can be partitioned into 2 disjoint sets with the same sum, if and only if y can be partitioned into 3 disjoint sets all with the same sum. Notice in particular that I'm not considering arbitrary sets y, I'm only considering the set y that comes out of that reduction. So in particular, I know that y contains this large element with 1/3 of the total value of all elements in y. Yeah. Well, if there were anything else together with that element in one of the subsets, say C, then the sum of all the elements in C would be bigger than that. But because all the sets have the same sum, I know exactly what the sum of the elements in C is. What I mean, that element is the size of, I've filled 3 boxes with toys, and one of my toys is precisely the size of a big box. So one of my boxes has to have that giant toy in it, and the other 2 boxes must be splitting the other 2. Okay.
Here's the proof.
There's the reduction. If there's a Hamiltonian cycle here, then there's a Hamiltonian cycle there. If there's a Hamiltonian cycle there, then there's a Hamiltonian cycle here. The other way is a little bit more interesting.
The other way, if I have some edges going in and others going out, I'm going to replace this with a vertex gadget where I'm going to label one end in and the other end out. So
each directed edge, each vertex is going to turn into this little path. Each directed edge is going to go from the out vertex of the tail to the in vertex of the head.
and then the argument is that first of all, if I take a Hamiltonian cycle in the original graph, I'll be able to sort of replace locally the passage
through this edge and that vertex and this edge, with this edge and through the chain, and then through not through that edge. So Hamiltonian cycle in G can be transformed into an undirected Hamiltonian cycle in H. You can't do it with two vertices because the other direction of the proof. Suppose I have a Hamiltonian cycle in H. It has to go through this middle vertex. If I didn't have that middle vertex, then I might go into this in and be back out, going along an edge backwards. So, but by forcing me to go through here, that means without loss of generality that I'm going from in to the middle to out. And then when I follow an edge out of this out vertex, it has to go to another in vertex. And so I get this sequence of in, middle, out, in, middle, out, in, middle, out, in, middle, out, which I can pull back to a Hamiltonian cycle in the original directed graph. Right, so this is one thing to be very careful about, is it's actually very common for people to write down reductions where the first half of the correctness proof goes through without any problem. And then the second half falls apart. And the reason is that the reduction was wrong. And so in that circumstance, what you get credit for is this. You got half of the proof, but you didn't provide a correct reduction, and you didn't get the other half of the proof correct. One of the other things I want to point out that's listed in the rubric, if you do the reduction the wrong way, you get a 0. So if I, for example, if I want to, there's this problem about box depth where I want to reduce box depth to maximum clique, right? That means I want to write an algorithm for box depth using an algorithm for clique as a subroutine. But if I attempted to write an algorithm for clique using box depth as a subroutine, first of all, it wouldn't work, and second of all, it's the wrong direction. You wouldn't get a proof. So if the problem says prove X is NP hard, and what you write down is, okay, great. Let's try to solve X by using an algorithm for SAT as a subroutine. That's backwards. I want to solve SAT using an algorithm for X as a subroutine. Okay. Yeah. Okay, let me strike this. Yeah.
To clarify language, so like a reduction of clique to box depth is
A reduction from clique to box depth would prove that box depth is NP hard.
great. Yeah, that's what I mean.
Yes. Unfortunately, box depth is not NP hard. So a reduction from clique to box depth also proves that P equals NP. So it's a worthwhile endeavor, but after the exam. Right. Okay. Well, okay, I'm happy to answer a question about LPs if you have one. Okay. So there's a question in the notes, which is a generalization of the question that you did on the homework. It says, okay, I've got a bunch of two-dimensional linear constraints, and I want to find a pair of squares that are as large as possible that fit inside this region. And what
I mean by as large as possible is I want to maximize the sum of the widths of the squares.
Okay. Two interior disjoint axis aligned squares with maximum total perimeter. Right, the perimeter is actually 4 times W1 plus 4 times W2, but whatever, that's fine. And there's a hint that there are 2 cases to consider. One of them is the picture that I've drawn here. The other is the picture that I can draw like this. Okay. So one of them is the 2 squares meet side by side. The other is the 2 squares meet top to bottom. And so what I'm actually going to do is describe a linear programming formulation for each of those 2 cases separately.
So I'm going to, this point I'm going to call L1, B1. This point I'm going to call L2, B2 for left bottom. Subject to what? Well, L1, well, I've got a bunch of these constraints. AX plus, A sub I plus X, A sub I X plus B sub I Y is less than or equal to C sub I, right? So these are my constraints. So I'm going to have, I have to show that this point is inside my rectangle. So A sub I L1 plus B sub I B1. That was a poor choice of, what should I call the y coordinate of the bottom?
Q.
Q. Okay, good. It's an upside down B. Q1 is less than or equal to C sub I. And then I have to show that the top left point on box 1 is inside the region, and so I have an inequality for that. I'm actually going to have 8 of these, right? So I'm going to have 8 sets of inequalities, one for each of those, for those 8 corners. And then I'm going to have one more constraint, which is L2 is equal to L1 plus W1.
Says the second box, and in fact I could probably even actually say greater than or equal to here if I wanted to be generous. This just says that the second box is completely to the right of the first one. Yeah. What? I'm not sure I understand what you mean by necessary. Well, only if the difference between L1 and L2 is the width of square 1. That's all that inequality is saying. W2 doesn't tell me anything about L1. Okay. And then the opposite constraint, if I want to think about the red case, would be Q2 is at least Q1 plus W1. And otherwise, I'd have exactly these same 8n constraints. So I have a linear objective function. It's the sum of these 2 variables. For each constraint, I have 8 in my input. I have 8 constraints in my output LP, 1 for each corner of these 2 squares. And then in one case, I add a linear constraint that says square 2 is to the right of square 1. And in the other one, I add a constraint that says square 2 is above square 1. And one of these two will give me the actual optimal solution.
Is there a rubric for linear programming problems?
There should be. Roughly, let's see. There'll be some, to make sure you have the constraints. So that some partial credit if you don't omit any necessary constraints. Some partial credit if you don't include any non-existent constraints. So just one constraint for is your objective function the right one? Are you doing max and min the right way? I guess that's really all the three of them there are. And then maybe there are some penalties for like your constraint function isn't actually linear. It's like you wouldn't want to maximize w1 squared plus w2 squared. That's not a linear function, but so you lose points for that.
And then in this case, what did you actually write down? So you have two functions.
So what I would write down is, here are two linear programs. The optimum solution to the problem you've given me is the optimum solution to one of these two. So you solve them both and take whichever one is better.
And we don't need to write them in standard.
Oh, no, you don't need to, I mean, these are all three variables.
Right.
But you don't, I mean, you could put them all on the left, but yeah, whatever. I assume that we can do that. Yeah. I'm sorry? If it asks for a linear program and you give an integer linear program, you haven't given a linear program. So, no. If it asks for an integer linear program and you leave out the integer constraints, then also no. Although in that case, I could say, oh, you forgot to write this down, -1. But if we say, give me a linear program, and then you have as one of your constraints, this variable is either 0 or 1, so that's not a linear program.
Do we need to know how to write the goal of a linear program?
No.
We don't need to know the syntax.
Not for the exam. For life, yes. But not for the exam. Okay. Let me get to the last chunk of the stuff, because I do need to leave pretty soon. So does somebody have a problem that looks like it might be a flow problem? Perhaps because it's in the flow lecture notes. Cycle cover. Okay, this is a good one. Okay, so cycle cover is, the problem is you are given a directed graph, and I want to find a set of cycles that collectively touches every vertex.
How about add in wrong direction?
Oh, yeah, okay, fine, sorry. That was the wrong one. Okay. All right, so my input is a directed graph. And my output, well, I mean, for purposes of the exam, my output is actually just going to be either true or false. But for the thing that I might actually want to compute is a collection of cycles in G touching every vertex once. Okay.
Is there a hint?
Bipartite matching.
Okay, so there's a hint, something about bipartite matching. So, what am I matching to what? Maybe a slightly different way of saying the same thing. I mean, bipartite matching is an example, the simplest example of an assignment problem. I have two different kinds of things, and I want to assign everything on the left to some corresponding thing on the right. Okay, so I want to assign x's to y's, whatever x's and y's might be. So maybe the thing to think about here is, what's an easy way to describe this collection of cycles? Then you return false. So suppose there is such a thing. How would you describe it in terms of data structure? Yeah.
Sets of edges.
Right. But can you be more specific?
Have a set of the edges of one cycle, a set of the edges of the other cycle.
Right. And how would you implement that? Remember, you've got a data structure that represents the graph. So you've got an array with one entry for every node, and you've got for every edge leaving that node, you've got a corresponding list of records hanging off that thing in the array. Maybe, yeah, that's your adjacency list data structure. Maybe you want to do something that uses the data structure that you're given as input as a way of storing this collection of cycles, or do you want to, rather than creating a brand new data structure from scratch? Yeah. I'm sorry? I don't know. Maybe not. Yeah, the answer might be no. There is no cycle cover. In which case, whatever your algorithm will eventually be, it should correctly return no. Right? Doesn't always exist. So what I'm really doing here is I'm assigning for every node v, I need to assign a node next to v. So I'm standing at v. Where do I go next? Well, v is part of the cycle, so I go to the next node in that cycle. So I'm assigning a successor to every node. A successor is just another node. So I'm assigning to every node, I'm assigning another node. So I'm going to build a bipartite graph where one side of the partition, I'm going to have a vertex for every node in my input graph. And what am I going to have on the other side of the partition? Same thing. Right? So if I have an edge in my original graph that goes from node U to node V, then what I'm going to have in this bipartite graph is, well, let's just to disambiguate, let me call these V plus and V minus. So here is node U plus, and here is node V minus, and I'm going to have an undirected edge going between these two. So every directed edge I'm going to turn into an undirected edge. Why? Because I'm assigning every vertex to another vertex. I'm doing an assignment problem. In an assignment problem, I built a big bipartite graph where I put the foo's on one side and the bars on the other. In this case, the foo's are the vertices and the bars are the vertices. Okay? And now
Okay, so build the bipartite graph H with V of H equals V plus union V minus. And the edges of H are all pairs U plus V minus, where U to V is an edge in the original graph E. And now find a perfect matching in H.
So a perfect matching in H means for every vertex on the left, I find a corresponding vertex on the right. That means for every node in my original graph, I successfully found a successor, and all those successors are different. And so I have a collection of forward pointers that describes my cycle time. Or another way of saying this is I have a subgraph of my original graph G in which every node has out degree 1 and every node has in degree 1. And that must be a collection of cycles.
Okay. So since I'm actually trying to return true or false, what I would really do is to say if H has a perfect matching, return true. Otherwise, I would return false. Okay, how long does it take to find a perfect matching if it exists? Right, so this is order V times E.
But remember, this is the number of vertices and the number of edges in H. So we have to be a little bit careful here. How many vertices are there in H? Twice as many as there were in G. And how many edges are there in H? 1 for every edge in G. So in fact, this is correct in terms of the original graph.
Does dependent have to be undirected?
Well, okay, so if I'm thinking about how I might solve the perfect matching problem, then the first thing I do is I have a source on the left and a target on the right, and I direct every edge from the left to the right. But the definition of the bipartite matching problem is I'm given an undirected bipartite graph. It'll be directed by the algorithm that solves the problem. The definition of the problem doesn't have anything directed. Yeah. You do not need to regurgitate any algorithm that we've seen in class. So just say, compute the maximum number of disjoint paths, edge disjoint paths, or vertex disjoint paths from S to T, using the algorithm in class, which ran in this much time.
Similarly, you could say H is perfect.
Yeah. I mean, what I wrote here
Is bad.
is the correct solution. Full detail.
Can we expect full problems with command?
No.
This might be a real stupid question. Because also when I'm assigning something, so what the flow, like the conversion that one you have to actually assign.
So, say the question again.
So like, I mean, recolor is also like kind of like assigning something.
Sort of, but the constraints are different. So with an assignment problem, the constraints are things like how many times will this object be assigned? Must be at most 7 or at least 3. But with 3-color, I don't have I'm assigning colors to nodes, but I'm not doing it in a way that says I can color at most 72 nodes red. The constraints are more combinatorial. I'm not allowed to assign both of these nodes red because they're adjacent to each other. And I mean, one way to think of it is if you can imagine immediately writing something down as like, how many times did you assign this as an inequality, then it's probably going to be a flow. But if it's any more complicated thing about the way that you assign things to it, then it's probably not a flow.
All right. I will put these up on the web before I leave.
Before we leave, so homework 10 grades are being released as I speak. Please submit your regrade as soon as possible.